Okay, so for lecture one today, what we're going to be doing is, let's see if we can get this off of there. We're going to cover some of the modalities and give you a brief history of medical imaging. And then we will start talking about some imaging concepts. And depending on how far we get, we might even start a little bit on x-rays. All right? And feel free to raise your hand if you have questions. So the goals of this course, it's called Principles of Biomedical Imaging. So we really do want to try to provide you those principles that are common across modalities so that you can appreciate what's common between different imaging modalities with the idea that some of you may be inventing the next generation imaging modality, and so it's good to have a firm foundation so you can be able to innovate and sort of figure out what the core principles are. So the way we're going to do that is we're going to focus on three major modalities: X-rays, computed tomography, and MRI. I will talk a little bit about research applications, and you'll find that the problems are not super, like, we're not going to be looking for pages and pages of derivations, but it is somewhat challenging for some people because it's actually the first time they've really had to apply math to solve engineering problems in a way that's not completely obvious. So you do need to think about it and think about how to apply the math in a way that makes sense. All right. So that's the idea, is try to help you develop those thinking skills. So the basic problem is here. So I don't know if I can move that somewhere else. Okay. So we have some objects. So in this case, just a picture of a human brain, and then it's going to go through some imaging device. And what we're going to find out is if we look at the data that's coming right off the imaging device, in general, it looks nothing like the object. Okay? So one of the first things we need to figure out is how does the imaging device work, and what is the data that's coming off, what's the raw data look like? So that's the first step. So we need to understand enough about the physics and engineering of the device such that we can understand what the raw data are. The next step then is figuring out how to go from that raw data back to a nice image. And so that becomes a reconstruction problem. So really there's two things. There's acquisition, which is the imaging device, and then there's reconstruction, which is sort of what you do in your computer. Although in the old days you did it by hand, but now obviously everything's on computer. Okay? So medical imaging as a field is relatively young. It's only a little more than a century old. Okay? So it's a relatively young field. Really, you could date the start of it to Röntgen discovering X-rays in 1895. Later, during World War II, ultrasound sort of became a modality. Then, after World War II, Bloch and Purcell discovered NMR, or nuclear magnetic resonance, and that was the basis for MRI. Although that wasn't discovered until 1973, how to actually use that concept to make images. In the meantime, Jeffrey Hounsfield developed the first computed tomography scanner, and quickly following that, in the 70s, people developed both human imagers for both CT and MRI. And so right now, if you go to a hospital, I mean, you are basically benefiting from all that engineering and development so that you can either get an MRI, a CT, X-ray, ultrasound, PET, SPEC, lots of ways now of looking into your body without having to cut you open. Okay? So X-rays were first discovered in 1895, and then he received the Nobel Prize in Physics for that in 1901. Supposedly, this is a picture of his wife's hand with a ring on it. I don't know if that's true or not, but that's what it's supposed to be. Okay. The basic idea behind X-rays is essentially it's a shadow method. So there's going to be some source here that emits an X-ray beam, and if there's anything sort of that can impede that X-ray beam, then that's going to create a shadow. Okay, so it's really just shadow imaging, but we'll get into the details of what that means. So this is an early X-ray imaging system. So here on the left, you have this big contraption here, and then on the right, before people really realized that X-rays were bad for you, they did a lot of things with them. So for example, they used to see if your shoes fit using X-rays. Okay, But what happened was in the I believe in World War I, a lot of the X-ray technicians came down with cancer, and so they started realizing that actually you probably shouldn't have too many X-rays. Okay, and those of you probably know that when these things were first discovered, like X-rays and radiation, people just played around with it. Like Madame Curie played around. They're just playing around with these radioactive sources and X-ray sources, and then a lot of them came down with cancer or other diseases. And so then slowly the recognition was that you had to be fairly careful with X-rays. Okay. So modern X-ray imaging systems look a lot nicer. And most of you probably have had a dental X-ray, which is super convenient and portable in some sense. So we're going to talk a little bit, respond about the first 2 weeks talking about X-rays and how do we look at it mathematically and what are some of the issues with X-rays. Then we're going to switch to computed tomography. Now, interestingly enough, the math behind this was discovered in 1917. Okay, so someone could have actually done this in 1917. And then in 1963, Alan Cormack, I believe he was doing radio astronomy, sort of reinvented this whole algorithm without knowing about radon's work. And in 1972, Jeffrey Hounsfield reinvented it all again. He didn't know about either radon or Cormack's work, but he actually applied it to medical imaging, and that's why he got the Nobel Prize for doing that. Okay, so he was actually, and later on they discovered that the math had already existed before, but he was really the first person to put everything together. So computed tomography is essentially, you can think of it as an extension of X-rays. And so the idea is, instead of just having X-rays, so in this case we have X-rays, the beams are going this way, down here, and we're looking at the shadow image here. You can imagine what happens if we rotated the beam and the detector. So here's the sort of the source, these are the detectors, and we just rotate the whole contraption around the object. Then we're going to get a different sort of shadow image, okay? And if we combine these two, these are called projections. If we combine these two projections, then we can actually form a really basic image of what's in there. And the idea is we do many and many of these, then we can sort of start forming our image of what's inside. So that was the key insight, is basically take an X-ray machine and rotate it around your object. And at every point, and once you got all that data, then you have to figure out how to put it back together to make a nice image. So, for example, the most simple thing you can think about is you have an X-ray source and you shine it through the object, you see what happens, and you can move the X-ray source this way to make a line through your object, and then you can rotate it around. Okay? More modern scanners, though, just have a point source that emits lots of rays, and so this is what's called a fan beam, which you'll learn more about, and they can go very quickly. So when Dr. McVeigh gives his lectures, you'll see that, for example, now X-rays are CT machines are so fast that you can actually get an image of a beating heart in like 1 heartbeat. Okay, so that's how fast they are. So this is an example here where you have the source, the fan beam, and then these are the detectors. And basically this thing just zooms around. Okay? So it's a real feat of both physics, electrical engineering, and also a lot of mechanical engineering, because you've got this big thing zooming around super fast. All right? In the old days, you'd go slice by slice. So if anyone was in an old, so if you're in an old generation CT machine, if you hear a whirring, and then the table goes, and then a whirring, and the table goes, okay? So that's like a first generation CT machine, okay? If the table goes continuously, and you hear the whirring the whole time, then that's what's called a spiral scan, and basically it's just doing a spiral around you. And if that takes, a minute or so, you're in an older generation. If the table just goes zoom like that, it's acquiring basically a spiral, but a big wedge of data the whole time, and so it can just go through your body very quickly. Okay? Yes, questions? Yeah, the answer is as few as possible. You should not just jump into a CT scanner just for the heck of it. So I think when Dr. McVeigh talks about CT, he'll go into a lot more detail. But in general, as with everything, it's suggests that you minimize it, and that's actually, um, you know, CT can do a lot of things, but it does have that downside. Now, at the same time, the technology is getting better, so people are finding out ways to do lower dose. So it is a changing landscape. So in general, the thing is, if you don't need it, you only do it for medically demanded reasons. So for example, if someone has a concussion, you'll get a CT because you're either going to die or you're going to get radiation. But if you're just like worried about do your shoes fit in your feet fit in your shoes, and that's not a good reason. Yeah.
Sorry, one more. Then why don't we use like rays that are less likely, like lower energy ways?
Oh, that's a good question. So we'll get into a little bit of that maybe today or next on Wednesday. But the idea is in there's a couple things in medical imaging that are sort of common themes. One is signal to noise. So basically, how much signal you have versus how much noise there is. Okay, and basically, and you've seen that. For example, if you have a really noisy image, it's not really useful. So you have to have enough energy so that enough X-rays get through, such that you can have a good image. Okay, so we'll show a little bit of that today, but that's the bottom line: is that if you have a really noisy image, it's not useful. Okay. So this is an example of one of the first 1975 commercial images. So it's actually pretty remarkable. This is a axial slice through a human brain, and I don't know why that keeps going off. And you can see basically there is a brain, and then these uh, this dark area here, that's your cerebral spinal fluid, your ventricles in your brain. Okay. But as you can see, with a modern scanner here, it's obviously much better quality. And you can see the resolution has gone from 128 by 28 here to now 512 by 512. And then with modern imaging, you can get these amazing pictures of the anatomy, and really 3D and 4D imaging is now standard. And so, for example, in here, does anyone know what this stuff is? What do you think that is? Yeah, it's a stent, right? That's someone's heart, and then they had to have a stent put around. They probably had a clogged artery, and so had to have that done. Okay, the last modality we're going to talk about is MRI, which, as I mentioned before, was the basic phenomenon behind that was discovered in 1946 by Bloch and Purcell independently, one at Stanford, one at Harvard, but they both came up with the idea about the same time and published in the same year. So relatively soon, they jointly received the Nobel Prize in Physics in 1952. In 1973, Paul Lauterbur published essentially it's a one-page article in Nature publishing the first MRI image, and this is what it is. So this is the first MRI image ever. It's an image of two test tubes. Okay, so not very exciting, but it showed that you could actually image using NMR. And this was quite remarkable because supposedly even in the late 40s and 50s, Bloch and Purcell were trying to figure out whether they could create images with NMR and sticking their heads in the machine or their hands in the machine and seeing if they could get anything. So NMR completely revolutionized chemistry. So the main use of NMR for almost 30 years was exclusively in chemistry, looking at chemical spectrum. But it wasn't until Paul Lauterbur, who was also a chemist, figured out that you had to do something a little differently that they were able to make images. Now, the interesting thing is, it wasn't like they didn't have the technology back in 1946. Bloch and Purcell could have easily done what Paul Lauterbur did in 1946. They had all the electronics and everything to do it, but they just didn't have the right idea. Okay, so a lot of times it's really having the right idea that's really important for some of these innovations. Okay, so it's not having the fanciest equipment, it's not having the most money, it's just having the right idea. Now, Paul Lauterbur had to wait, I guess, 30 years to receive the Nobel Prize for this, and he shared the Nobel Prize with Sir Peter Mansfield, who did a lot of additional work in the 70s. And there's a whole story behind that. There was a third guy who wanted to get the Nobel Prize. And there was a big fight that went on for decades about whether he should be part of the Nobel Prize as well. Ultimately, he did not. This other guy, Demadian, did not get the Nobel Prize. He was really pissed off, put a whole ad in the New York Times, I think, complaining about it, but still didn't get the Nobel Prize. Okay. And they were really worried because I forget, Lauterbur died not soon after he got the Nobel Prize. So there was a real rush to make sure they got the Nobel Prize to him before he died. So after Lauterbur's first discovery of MRI, there was a lot of work in the 70s, mostly in England actually, with these weird contraptions. So these are sort of the first MRI, human MRIs. But what really took off was in the 80s when the major manufacturers like GE and Siemens and Philips got together with the academics and really came out with the first MRI systems. And MRI is actually really interesting because of all the modalities, it has the most academic research because it came out of academic research. And so even to this day, the meetings are mostly people from universities and people from industries, and we work together very closely. So there's been a lot of innovation. In fact, when we talk about MRI, a lot of the innovations in MRI over the last 20 years have come from graduate students like you. Okay. And then in 1993, the next big revolution in MRI was the discovery of functional MRI, where you could use these MRI machines to actually look at the brain in real time. And that totally revolutionized the study of psychology and psychiatry. Okay. So whenever you see a picture of the brain with some spots, colored spots in it in the news, that's functional MRI. So the MRI system looks a bit like the CT system in that it's sort of like a donut shape, long donut shape, but it is a little different in the sense that what we really have here, the main thing is this huge magnet, and we'll talk about how big that magnet is when we talk about MRI. But these are magnets that are like 30,000 to 60,000 times the Earth's magnetic field. So really, really strong magnets. At UCSD, we have a number of these 3 Tesla magnets, but other places in the world, for example, here at the NIH and also in France, are building these huge magnets. I don't believe either of these are working yet. They're just really feats of engineering. But see how big this magnet is? Like, there's just the person here, and that's the magnet. Okay, so these are huge things. All right. So MRI, one of the things about MRI is you can actually design it so you can, there's a lot of different ways of using it. It's almost like the Swiss Army knife of medical imaging in that depending on how you program it, you can get different images. So for example, these are 3 different images from the same brain acquired in the same scan session, each giving you slightly different information or different contrasts. Okay? So when we get to MRI, we'll talk a little bit more about what each of these contrasts means. This is actually from Professor McVeigh's lab a while ago, where here there's something called cardiac tagging, where you can actually use the MRI to get the protons to line up in lines. So for example, here you see these nice lines, and those are actually imposed in the tissue. And therefore, as the heart deforms, those lines will deform with the heart. Okay? So what might that be useful for? If you were able to do that, what could you use that to measure? Yes?
You can measure elasticity of the heart and shear stress.
Yeah, things like stress and strain, right? So this is something where a method for doing that. And this is something that's, I find, still quite remarkable, which is basically, I could take any of you over to our center about 10 minutes from here, put you in the scanner, and like within 8 minutes, come up with an image of like that, which is basically the wiring of your brain. Okay. So this is something called diffusion tensor imaging, which we'll talk about later on in the course. And it's really the foundation of a lot of huge studies going on now where we are essentially mapping the human brain and seeing, for example, how different things are connected and how that's affected with different diseases or disorders. Okay. So that's it for sort of the overview of modalities. So before I switch into some of the more imaging concepts, are there any questions? Okay. So what we're going to do today is we're going to review some of the imaging concepts. So this is covered in chapter 3 of your book. I'm going to go about it slightly differently than they do, but the main concepts are the same. So first, some basic terminology. You will hear certain there are certain planes that we acquire for the human body, the images in. So the most common one that you'll probably see is what's called axial, which is basically just cutting this way. Okay, so this is, for example, an axial scan. Okay, so that's the images you typically see in like in the news. Now, if I cut this way and acquire slices this way, that's what's called a coronal image. Okay, and if I do go this way and do slices this way, that's called a sagittal image. All right, so that's just some basic terminology to have. There's lots of different ways we can look at the data. So essentially, we can imagine we have x, y, z coordinates of our volume, and at every point we have a number that represents something about our image. So we just take a slice. So if we just think about x, y coordinates, the most common way is just to display it as like a grayscale image or even a color scale image. Okay, but sometimes people do like to display it maybe sort of more like as a function plot, where the third coordinate is sort of the amplitude. But by far, for this course, mostly we're going to be focusing on looking at things in this manner. And the third basic thing we want to talk to you about is just simply what we mean by volumes and slices and pixels and voxels. So, volume is just like a 3D volume that we're going to look at. One cut through it is a slice. Okay. Now, when we look at the image, it looks like pixels, right? But we have to remember in your back of your mind that that came from a slice, which actually has a thickness to it. So it's actually a 3D little pixel. The pixel is representing something that's in a 3D little cube, and we call that cube a voxel. All right, so you'll hear the word voxel a lot in medical imaging. Okay, so the first concept we want to introduce to you is contrast, and any of you who's played around with your display on your computer already knows about contrast. Essentially, contrast is a way of saying, how much does the image vary across space, or it could be across time later on when we look at time series images. But the basic idea is that we're hoping to get some information due to contrast. If there's no contrast in an image, like if we look at the image here, this basically carries no information, right? So there's no contrast in the image, there's no information. So we want to have some contrast. So for example, this is a X-ray image of someone's chest, and you're looking at across this line here, you're seeing how the image brightness varies as you go across that line. These are some pictures that Professor McVeigh made up last year. What you're looking at here is for some CT images of a phantom. So the other word we'll use is phantom. Okay, so phantom does not refer to like a ghost. Phantom just refers to a just an object that we put into the system to characterize its properties. All right. So there's MRI phantoms, there's X-ray phantoms, there's CT phantoms, and there's different kinds of phantoms. Okay, so that's what we mean by phantoms. So this is a phantom that has a lot of little dots in it of different sizes and spacings. And so you can see here, across this row here, there's pretty good contrast, right? You're seeing that you can sort of see the up-down modulation fairly well. You can sort of see here that if you look at the same row here, there's really not that much contrast. Okay. So what else has changed between these two images, between the top and the bottom? What else do you see that's different between these two images? Noise. Yeah, this definitely looks a lot noisier than the top one. So the concepts we're going to talk about, contrast, signal noise ratio, resolution, they're all sort of linked together in terms of how good the image looks like. Right. Oftentimes we're going to talk about something called local contrast, what the book calls local contrast. So that might be you have a background and you're trying to look at like a little nodule or a little tumor on that background. So for example, here you could easily tell that there might be a tumor. Here you'd be very hard pressed to tell that there's anything there. Okay. So contrast is very important when you have the radiologist looking at your image and trying to decide, is there a tumor there? Has it gotten bigger? Has it gotten smaller? How did it react to chemotherapy? So typically the way they define contrast is you'll define the background, which is sort of a uniform background, and then you'll have your target, which is what you're looking for. And the contrast is simply the difference between the target and the background divided by sort of your average background level. So that's what the book is defining as local contrast. So here's two examples of local contrast, where here you have fairly good local contrast on the left. So you can really sort of see that dark spot. And here, especially, you can sort of still tell there's something there, but it's a lot harder to tell. So there's much less contrast in this image. All right? So clearly, you would want your diagnosis based on this. You would hope that the radiologist or the radiological technician has done their best to set up the imaging system such that it offers the best contrast. Yes?
So for the local contrast, is the background the average background of the region?
Yeah, so it's basically this is where things get a little murky, like what's background and what's not. And basically, in the real world, you just use your common sense. Like you look at it and go, okay, well, this looks like the background, and you sort of define an area and say that's background. And then you can maybe come up with automated algorithms for that, but it varies. Yeah. Okay, the next thing we're going to talk about is resolution. Okay. So resolution is essentially how blurry your image is looking at. And so the first, we're going to talk about a couple different terms, but they all refer to the same thing. And the first one, which is sort of the more systems term, is impulse response. Okay, and we'll talk about impulses a little more Wednesday or next Monday. And that's basically if you imagine putting a little point, imaging a little point. So here this is the point we're trying to image. And you're looking at what does that point look like after you use your imaging system. Okay? So that is called the impulse response. Right. Now the other names for it are point spread function. So essentially you have a point, how much does it spread? And also line spread function. That's simply because when you actually design these, when you actually want to go and measure something like this, it's hard to just make a point. So typically you'll have a little wire through your phantom to make a line, and then it's how much does that line get spread out. If you're looking at the line head on, how much does it spread out in the transverse plane? Okay. So these are some examples here. So this is your point stimulus, which is probably if you could make a point, then this is how it'd be spread out. And in general, you would actually have a wire, and you're looking at in this plane, how does that wire get spread out? Okay. So that's all. So you'll hear the term point spread function or line spread function sort of used interchangeably. Okay, so for example here, we have a lot of little points here, okay? And so the idea is how much do each of these little points get spread out? And you can sort of see as we make these dots smaller and smaller and put them closer and closer together, it's going to be much harder to tell them apart, okay? And so that's sort of defining what our resolution is. So the typical way that you use to define point spread function is what's called full width at half maximum, or abbreviated FWHM. Essentially all you do, and here the assumption is you have a rather smoothly falling off function, okay? And so you look at its maximum, okay? You take half of that, and then you measure the width at that half maximum, and that's the full width half maximum. Okay? So if you are spaced at your full width half maximum like this, okay, typically that's the limit at which you can tell two dots apart. Okay, so if they're any closer than the full width half maximum, they'll merge into one dot. If they're farther than the full width half maximum, then in general you'll be able to tell them apart. All right, so that's just a good sort of what the field has sort of picked as one way of characterizing resolution. Now the other way to think about resolution, and I know some of you haven't done Fourier transforms in 2D yet, but we're going to try to introduce them now, which is basically we can also think about images as being made up of sinusoids. Okay, and so in this case, this is figure 3.1 from the book, where you have sinusoids at different frequencies. So either there's no variation here, so this has 0 frequency, and here you have very high frequency. Okay, so for example, here you can see the period is from there to there. So a period of 0.5 there, and or this period of 1 here. So I guess this spacing is 1. Although this with MB of A, MF equals B of A. Yeah, no, sorry. Actually, these all have the same spacing. They're all the same frequency, but they're just changing the modulation. Okay. So basically, the idea is these are all the same frequency, but depending on how big that modulation is, how big the amplitude of the sinusoid is, the more you can actually see it. Okay. But the idea is the other way you can characterize a system is you can put in frequencies of higher and higher images of higher and higher frequencies and see how well they're imaged. So for example, the way you might do that is you might have these phantoms, whereas you can sort of see the spacing as we go in this direction is getting finer and finer. So we're having higher and higher frequencies as we go in that direction. And same thing with this star pattern here. Okay. So what we can do is you can imagine, so that's we're going to come up with something called the modulation transfer function or the frequency response. Okay. So the idea is you're going to put in a sinusoid of different frequencies. So here 0.5, 1, 1.5, 2, 2.5, and 3. And they each have, let's say, full amplitude. Okay? So you put that into your system, and then you see the amplitude that comes out. So in this case, at a low frequency, it goes from 100 to 96, and then it goes down to 85, 68, 48, 27, and 7. So as my frequencies get higher, they are being more attenuated. And if I plot that as a function of frequency, that's what's called the modulation transfer function, or the MTF. All right, so it's another way of looking at resolution, which we'll get into in a minute. So here's an example from the book. So these are 3 images of X-ray images of someone's hand. And in each case, what's shown below in the second row is the modulation transfer function. Okay? So for example, you see here that all of them have this sharp drop off as our frequencies get higher. But this one drops off much more quickly, right? So that's a very fast drop off. So it's really attenuating those high frequencies. So what do you see, what can you tell about these images as we're going from here to here? What can you see if you can see it there or on your devices? What would you say qualitatively is happening with those images? Does it look better on the left or on the right? Left. Okay, so what's better about the image on the left? Okay, and what do you mean by that? Like like if you didn't know the word resolution, you try and explain this to like a 5-year-old, what would you say to look at? Yeah, it's a lot clearer, right? Yeah, were you going to say something? Okay, okay, right. So another way we could say it, it's more blurry on the right side and much more clear. Essentially, this basically a little bit out of focus on the right and in focus on the left. Okay, so what we say is the resolution on the left is much better than the resolution on the right. Okay, and if we look at the MTFs, which has the broadest MTF? The one on the left, right? So the broader my MTF, the the more frequencies I'm letting through, and so I'm going to get more information. Okay, so that's the MTF. Now we talked about the point spread function. So let's just assume that I drew the point spread function. I said the point spread function for this guy is like this. Okay, so that's what a dot would look like for the system on the left. Now, what if I were to draw the point spread function for the system on the right? Should it be narrower or fatter than that? Okay, it should be fatter, right? So the point spread function for the one on the left is probably like that, right? It's going to be fatter. Okay, so that's the other way. So you can look at it in either domain. So this is the signal domain, and this would be the frequency domain. Okay. So what else do you notice about that? As the modulation transfer function is getting narrower, what's happening with the PSF? Being fatter, right? So this is basically sort of time frequency or space frequency duality. As you squeeze things in one domain, it gets fatter in the other domain. Okay. Some of you may have heard like the uncertainty principle in physics. Same thing. Okay. So so this is a concept we're going to come back to over and over again, but this is sort of your first intro to that concept. So here again, so just to sort of drive that point home, what I've drawn on the left, what's shown on the left is 3 different line spread or point spread functions, and on the right are their modulation transfer functions. You can sort of see that uncertainty principle at play there. As one gets thinner, the other has to get wider. Okay? And then we're trying to introduce some terminology here. So for example, h of x is my impulse response here, or my PSF, or my line spread function. Okay? And that's basically, I'm going to put my impulse. And here we're introducing the notation for what's called a Dirac delta function. Okay? And so it's saying I put my delta function through some system, L, here, and my output is simply my impulse response. And now I'm saying my h of f, which is my modulation transfer function, is going to be the Fourier transform of my impulse response. Okay? So we'll get into that more, but this is sort of where we're headed in terms of how do we take these sort of concepts and start applying some math to them and using that to design systems and understanding how systems work. Okay, so let's do an experiment here. So the website you want to go to is pollev.com BE280A. If you can try that, there is now a poll that should be viewable. And let's do problem 10. So basically, there are these different, let's see. Okay, so this shows different LSFs. And we want to say what MTF corresponds with C. So you have choices of MTF 1, 2, or 3. Okay, does everyone see that poll? Can you log in? Okay. So go ahead and just take a few minutes to do that, and we're just sort of testing out the system today. So the system lets you change your mind, right? Is that right? Okay, good. Okay, because I see some answers changing. Yeah, go ahead.
Do we need to log in and sign up to your
No, not for today. Yeah, don't worry about it. Today we're just testing things out. Yeah, in general, I mean, just to give everyone concept, I mean, for any exercise that's done in class, there's not going to be any sort of judgment on whether you got it wrong or not. It's really just, did you actually participate? So you should feel free to just guess whatever you want to guess. I mean, obviously use your, try to apply the concepts from the class, but don't worry about participating, right? The only things that are graded are the homeworks and the quizzes and the final. Okay, so let's take a look here. So first of all, I'm glad there were only 2 answers that were chosen, either 1 or 3. So that's good because obviously it has to be one of those. It can't be the middle one. So that's good test taking skills. So you've actually boiled it down to now you have a 50% chance of getting it right. And most people did get the right answer. So the right answer in this case was 3, right? Because of what we just talked about. We have C is the narrowest point spread function. So therefore, it has to correspond to the widest MTF. Okay? Any questions? All right. Okay, so now let's talk a little bit about noise. So noise is just a fact of life. So there's noise, and there's different types of noise, but no matter where you go, there's always something called thermal noise, which is just the random motion of molecules. Okay? And so that affects both the electronics, but it also affects the sample you're looking at. So for example, if you're looking at anything like a human body, there's lots of just random currents going around all the time. So an MRI system will actually pick up all that noise as well. Okay, so there are sort of it's not something that even if you design the best system in the world, you're still going to get noise from your sample in many cases. All right. So this is just showing that obviously as you increase the noise, the image gets worse, and at some point it becomes unusable. Okay, so probably this is still okay. This is probably unusable, and that's definitely not usable. Okay. So there's different definitions of signal-noise ratio that are talked about in the book, and we'll revisit them in the course. The main one we'll do is what's called the amplitude SNR, and that's really just the signal amplitude over the noise amplitude. Okay? And probably the most important thing to remember throughout your whole life as an engineer is SNR is proportional to the square root of time, which means SNR is incredibly expensive, right? Because remember, time equals money, right? Okay, so that means if I want to double my SNR, how much longer do I have to scan? 4 times as long. Okay. The same way, let's say I have a scan. Someone's saying, um, basically, I have my scans 10 minutes long. I'm like, no, no, no. I need my scan to be 5 minutes long. So I'm going to half my acquisition time. What happens to my SNR? It's going to go down by roughly how much? Like 30%, right? So square root of a half, right? So it's really just very, SNR is something that it's really important because it's proportional to time, but you want to do your best to have the best SNR possible. The other SNR that's talked about in the book is the differential SNR, or sometimes called a contrast to noise ratio, CNR. So contrast to noise. Okay. And that is essentially similar to local contrast, where you have some target, you're comparing it to a background, and you want to see how much contrast you have with respect to that, to the noise level. So as we talked about before, there's really just everything is related. Okay. So for example, there's resolution, there's noise, and they all sort of and there's contrast, and everything works. It's all in there, and we have to sort of keep them all in mind as we're looking at images. So this is an example where here we start off here with no noise here, and so these images are just showing you the effect of blurriness. Okay. And then here we're increasing the noise this way. Okay. But let's say we took a really noisy image and blurred it. Does that get better? The blurring is actually helping a little bit, right? Because it's averaging out some of the random noise. And so there's always just going to be this trade-off between how much, how do we trade off resolution versus noise versus time versus money versus contrast? Okay? So these are some of the topics we'll be talking about. The other topic that we're going to be talking about is sampling. Okay? So everything is digital now. I mean, everything for X-rays still somewhat analog. You can still get a film, but most places, like at the dentist, have gone digital. CT is definitely digital. MRI is digital. Everything is just numbers. Okay, and it takes time to acquire each number. Okay, so just like when you're buying your TV or when you're buying your computer, the more resolution you want, the more it's going to cost you, right? Either in terms of internet speed, how much, how many bits you want to acquire, what screen size you have. Same thing with medical imaging. You actually have to, for every additional piece of information, you're paying for it, either in a better machine with money directly or with time, because it's going to take you longer to acquire that information. And in some cases, it's okay. Maybe the subject can lie there for 10 minutes or 20 minutes. In certain cases, you actually even don't have that option. Like if someone is dying in an emergency room, you've got to get them in and out. If they have a stroke, you might need to make a decision rather quickly as to what do you do. Okay, so there are some life and death situations where you deciding on how much information to acquire. It's like, I need an hour of information. No, sorry, if you do that, the subject will be dead. Okay, you only have 10 minutes to acquire the information. All right. So that introduces sampling. It's like, how many samples do you want? So you might have a lot of samples, like in this case, or you might have fewer samples. And they're more farther spaced apart. So this is an example from the book where they've taken, and it might be hard to see here. So if you look at it on in your red shelf, you'll be able to see this image better. But what you'll notice is if you go from this image to this image, you'll notice here there's some weird stuff that's been introduced that's really not in the body. Okay, so that's what's called an aliasing artifact. Okay, so that's something that we'll talk about when we talk about sampling, and the idea is you always want to avoid introducing things that are actually not in your image. For CT, just to give you an example of what the requirements are or how we think about these things and the effects of it, in CT, for example, if we just take a very simple example, we can decide how finely apart we want each X-ray line. You know, how many X-ray lines do we acquire? And then also how many angles do we acquire? Do we advance by a degree at a time or do we do 10 degrees at a time? All these things have an effect on our image. So for example, if this is what the image should look like, if I either decrease the number of detectors or decrease the number of angles, you can sort of see we're introducing all these weird artifacts into our image. Okay, they look pretty cool, but you don't really want to have them if that's your body that's being imaged. Okay, so we're going to have to understand how do we make some of those trade-offs. We want to sample as little as possible so we can shorten the amount of time, but we don't want to sample to the point where we introduce artifacts that are going to make it hard to make a diagnosis. These are some other examples of artifacts. And so, for example, here you see there's a lot of interesting line artifacts coming out of that object, where there was too much spacing between the X-ray lines, and here there were not enough angles, and so you're seeing all these artifacts over here. Okay. And there's lots of interesting artifacts in medical imaging. These are just some more examples from the book, which we'll probably not get into in this course because it's a little more hard to analyze. But what we will talk about is something not related to sampling, but is just sort of due to sometimes the physics. You have to understand the physics of what's going on enough to understand some of the artifacts. And so, for example, this is something related to magnification, which we'll probably pick up on Wednesday. And here you have an X-ray source in both cases, imaging the same object, but in this case, there's two little tumors in the object, right? And in one case, those tumors look like circles on your X-ray. In the other case, this one, for example, looks they have different shapes, and all you've done is you've just sort of turned the shape of those objects within your body. Okay, so sometimes being aware of the geometry and the physics is also important for understanding how artifacts or distortions come into the image. All right. So we're gonna, that's it for, let's see, yeah, so this lecture ends here. So what we're gonna do is see if there's any questions, and then we're gonna spend about the last 20 minutes setting up X-rays for next time. Okay, so are there any questions? Okay. Okay, so today what I want to do is just go through some of the basics of X-rays, and then next time we're going to start talking about how do we sort of introduce some math and start understanding X-rays. So X-rays, we start with X-rays because it's really the simplest one to understand. You know, everyone sort of has had experience probably with an X-ray, and anyone who's done any like shadow playing, you know, doing hand shadows, you understand the basic principles of X-rays. Okay. So you already have some physical intuition about how X-rays work. So what we want to do in the next week or two is just sort of add some math to your intuition. Okay. So whether you're doing X-rays or hand puppets, you can apply this theory to that. Okay. So basically, we have a source. So an X-ray source, or it could be a flashlight. We have our object, and then we have the display. So X-ray film or the wall or something like that. In any case, it's what's called a projection method. You're basically looking at shadows of your object. Now the question is, how do we go from that simple understanding to a sort of more sophisticated understanding? So the parts we're going to talk about are how do we produce the X-rays? How do the X-rays interact with our body? And then how do we measure what comes on the other end? Okay, so those are three main parts of the X-ray imaging chain. just to give you guys some perspective, what we're talking about with X-rays are things way up here, very, very 10 to the minus 10 meters, so very short wavelengths. Okay, so for both X-rays and CT, we're talking about basically radiation. Okay, when we talk about MR, we're going to be down in this regime here, radio waves and microwaves. Okay, so luckily with MR, at least as far as we can tell, with all the safety limits, there doesn't seem to be any adverse effects. I have colleagues and I myself have been in the MRI scanner for hours and hours, and so far we don't have weird things growing yet, but keep our fingers crossed. So that's just to give you a sense of the difference in energy. That's what we're talking about. So how do you make X-rays? It's actually a pretty, it's a lot of power, a lot of heating, pretty messy process. Essentially, you're going to have a tungsten filament, and you pass a lot of current through it and heat it up. Okay, as that wire is heated up, it's going to have a lot of electrons just emitted from it. You're going to then apply a voltage, which is going to accelerate the electrons, and they're going to slam into your anode, okay, which is usually also tungsten, and that those electrons slamming into that material then give off X-rays. So that's your X-ray source, and it's heated up to a very high, 2200 degrees C, just by passing that current through it. Okay, so there's two things. One is obviously the more current you apply through this, the more emission there's going to be, and the more voltage you apply to this, the more acceleration there's going to be. They're going to slam in a lot harder into your anode. So a lot of those transfers just all they do is cause heat. So that's not very useful. Okay. The interactions we really care about are two. One is you can have the electron can hit an electron in one of these inner orbitals, and then as an electron from an outer orbital drops into that space, that dropping gives off an X-ray with a certain frequency. So those are called characteristic X-rays, and that'll be at they'll appear as little peaks in our X-ray spectrum. Okay, but by far the biggest source of X-rays is due to what's called Bremsstrahlung, or braking radiation, which is basically as the electron is coming close to the nucleus, it interacts with the nucleus and changes directions. And as it's doing that momentum change, it gives off some energy. Okay, and so that's what you're going to see. So typically, what we look at is X-ray spectrum from a tube. So these sharp lines here are the characteristic radiation. That's due to knocking out an electron and then another electron dropping down, and that transition gives you these sharp lines. All this other stuff, these bigger curves here, are the Bremsstrahlung radiation. So you see that's the major source and that's over a broad spectrum. Okay, and you can see here that what I'm doing here, each of these curves here corresponds to a different voltage I'm applying. So as I crank up the voltage, I get different curves. Okay, so the endpoint tells you what voltage was applied. So in this case, I applied 120 kilovolts of energy. Here I only applied maybe 45. Okay, so that's one dial you can play. And you'll notice that all these lines sort of taper off this way. Okay, which is sort of funny. You'd expect there to be a lot of low, and these are low energy X-rays. And what happens is all these low energy X-rays don't have enough energy to get out of the filament or the device, so they get absorbed somewhere else. And so this is a very characteristic curve where all the low energy stuff, and that applies not only to the device but also to your body. So for example, if I put low energy X-rays into your body, it's heating up your body and causing damage, but none of it's getting through to the film. So that's actually not very good for you. Okay, so we actually want to limit how many low energy X-rays we put into the person. All right. The next thing we're going to talk about is the interaction of the X-rays with the body. And so there's two main things that we have to consider. One is the photoelectric effect, and the other is Compton's scattering. Okay, and for most medical imaging, by far, this is the photoelectric effect is what we uh, see the most, and actually what we want to have happen. And essentially, the photoelectric effect is such that we come in, and as the X-ray comes in, it basically gives enough energy to an electron so it can escape from its orbital, okay, and it goes off and might get absorbed somewhere else. But essentially, from the point of view of our imaging system, it's almost as if X-ray just stopped there, okay, and caused some other stuff, but a lot of those stuff got absorbed. And to the extent that it gets absorbed, we don't have to worry about it anymore, okay? So that's sort of nice because we don't have to think about what angle it's going off at. The other kind is Compton scattering, where the photon can come in and then change directions, okay? And that's sort of a problem for medical imaging because imagine you had, let's say I was imaging this thing here, right? And I wanted to create a shadow image of this. But as the rays are coming in, if they just go off at random directions, then it's really hard for me to understand, to recreate what actually happened to make this image, okay? So this is just emphasizing once again that photoelectric effect is typically what we see at the low X-ray energies that we deal with for in vivo imaging. Compton scattering happens at higher X-ray energies, and it's something that we try to minimize. So this is just showing you here what's the total contribution to the total attenuation coefficient in soft tissue. We'll define what we mean by attenuation coefficient in a few minutes, but basically it's how much does it stop the X-rays, okay? So you'll notice here that below about 10 keV, it's mostly the photoelectric effect that's absorbing all the energy from the X-rays. Once we get about 30 keV or so, then the Compton effect starts taking over. Okay. So this is what an X-ray imaging chain might look like then, in a very schematic version. You have your X-ray source. It's giving off X-rays. You're going to have a low energy absorbing filter because we talked about we want to sort of get rid of those low energy X-rays that are just going to heat up the body but not help us create an image. There'll be a collimator to sort of get the X-rays to be sort of more in a beam. It's going to go through the body, and then there's going to be this collimating scatter grid here before it gets to the X-ray film. And you can sort of see what this is doing is it's trying to reduce Compton scattering. So only things that sort of go in a straight line can make it through, and it's trying to reduce anything that sort of goes off line. Okay. X-ray film, you will still see that some places, and so essentially that is something where just the chemical transition of the X-ray makes it such that the silver changes composition whenever it is exposed to X-ray. Okay. And another part of it is sometimes to make the X-rays have a little more signal to deal with, we will pass it through what's called an intensifying screen, or which is like a phosphor layer, which basically for every X-ray that comes in, it just sort of amplifies the amount of light that is emitted to the film. Okay. But now, in this day and age, things are much more going towards, digital tomography or radiography. So the first step is what's called computed radiography, where basically instead of having the film, you have an imaging plate which changes compositions when it's exposed to the X-rays. But then you have a laser beam that comes through and scans it and sees where it was changed, and then you feed all that numbers into a computer. So you just have a computer image. Okay. Otherwise, you have to have this film and carry it around everywhere. And that's sort of, not very convenient. So that's what a cassette looks like. So they make it. The nice thing is they can make it sort of the same dimensions as an X-ray film, so the technologists feel like they're just doing the same thing. But in fact, what they do is they take this cassette and then they put it into that scanner later, and then all the images go into the computer. But really what's happening now, especially, for example, when you go to the dentist, that's not done. You basically now have these direct digital converters, where essentially as the X-ray energy is coming in, it is immediately converted to electrical images, digitized, and then you have your digital image right away. And so that's certainly where things are going. And so, for example, that's an example where you can actually now just get this device here, which I think you just hook up to your laptop and take an X-ray and be done. Okay. Okay, so let's talk a little bit about attenuation. So we have in X-rays, we want to talk, there's something called the intensity of the X-ray beam, which really both is energy. So higher energy X-rays have more intensity, and also how many photons, or the photon fluence rate, how many photons of am I getting per unit area and per unit time. Okay. So the intensity of a X-ray can either be, you can either look at a single energy, or you can integrate over a band of energies. And so that's the difference between what's called monoenergetic. So for example, so here we're talking about polyenergetic, which just means you're looking at many energies, or you could look at monoenergetic, where you look at just one energy. But the main concept, which we'll end with today, is just attenuation. And that's the whole key behind X-rays and CT, is that not all the X-rays that come in get out. Okay? And the difference between the spatially varying difference in attenuation is what gives you your image and which gives you your information. So let's assume we have a single energy X-ray going through a homogeneous object here. So what we say is that the output intensity is equal to the input intensity multiplied by an exponential factor. That is e to the minus mu, which is our linear attenuation coefficient, multiplied by how thick the object was. Okay, so the thicker the object, the more distance it has to travel, the more it's going to get attenuated, or the higher the attenuation coefficient, the more it's going to get attenuated. And so this is an example here where through each thin slab, each time I go through one of these thin slabs, I'm losing 20% of the intensity. Okay. So I'm not going to go through the math here. This is in the book, but essentially the bottom line is, if you just assume that, per each unit length, you're losing some photons, then it just comes down to a first order differential equation, and that's what gives you this relationship here. Okay. So the only thing you really need to remember to do any of the problems for X-rays, at least doing attenuation, is just this e to the minus mu times delta x relationship. Okay, so fairly simple, but you should know it. Now, that's assuming that here we assume that mu was constant, right? In general, mu is going to be not constant. Okay, so it can either vary across your image or through your image. Okay, now through your image or through the slash, so let's say this is my slice, I'm imaging this, or something a little thicker. So there can be attenuation varies this way and also this way, right, in all directions. So in X-rays, we typically ignore how much it's varying this way. Okay. Basically, anything that happens through here, it's going to cause, it's going to be integrated over all of that. So we're just going to get an integral of that. So that can cause problems. For example, like if your heart, your heart's behind your ribs, so you're going to see your heart and your ribs on top of your heart sometimes. And so there's going to be overlap of things. Anything that was through that path, you're going to see on your image. Now, so that's because the fact is that your intensity is sort of related to the integral of all the attenuation that it sees going through this object. All right. Now in CT, we're actually going to invert that and figure out how to solve for that. Okay. But for X-rays, we're not going to worry about what's through that object. And the other thing you can do to get even more complicated is you can look at all the different energies, but we're not really going to talk about that too much in this course. Okay. So what we are going to end with is we're going to set you up, show you this, and set you up with a problem to think about. And on Wednesday, we'll start off with a sort of a poll to sort of see what you thought about it. So this is showing you the attenuation coefficient of bone, muscle, and I guess soft tissue here. And in this case, fat, I guess. And you can sort of see that different objects attenuate differently. So bone has the most attenuation. It's the most dense, and so it's going to stop the X-rays the best. Then comes muscle, then comes soft tissue. Okay. And these are some of the attenuation coefficients here at different energies. We'll skip over this for now. So so we're just going to skip to this last slide. So this is the question I want to leave you with, and we'll pick up with this on Wednesday. which is given this curve, and you want to say get the maximum contrast between bone and fat, what energy should you be operating at? Okay, so that's your first design problem for the quarter is you have a choice of these 4 different energies. Okay, which one should you pick? All right, so I'm going to leave you with that question. We'll talk about it at the beginning class on Wednesday. As I said, I'll try to post these to YouTube, and I'll send out a link if the recording works out. And I'm going to move to 161 in case you have any administrative questions for today. Just look for me there. Okay, thanks.